afternoon. So this is your second lecture. So today I would like to highlight on this term signal. So what is a signal? A signal is something which is a function of an independent variable and it carries information. So function of one or more independent variables and it carries some information. Say in our day-to-day lives we give some kind of gestures as a signal. Say this means you lost the match, this means you are in or victorious. So when we represent something mathematically, it becomes a signal, and we are interested in this kind of a signal where this indicates the amplitude of the signal and this indicates the variable, the independent variable, which can be time, which can be space or anything. So far we are concerned with temporal signals. Temporal signals means signals which vary with time, whose amplitude are a function of time. Now what are the types of signal? So in today's world, whatever I am speaking, I am giving some information. So that is a speech signal. A signal can be any biomedical signal like an ECG signal, or a signal can be a function of space like an image. So signal can be anything, as I said, a function of one or more independent variables. Here we are focusing on time and it carries some information. So in electrical engineering theme, we say signal, or we describe signal as an electrical quantity, that is a current or a voltage, a time varying current or a time varying voltage. So physical signal can be in any form of energy, like speech is in the form of sound energy. So we need to convert this information into the domain of current or voltage through something called sensing. So there are sensors and transducers which produce these currents and voltages, and while producing them we encounter some kind of noise in the signal. So the main objective of signal processing is to filter out the noise and get the useful information. Like when I am speaking, so somebody might be recording my audio, so there are other forms of noise which are coming in. So the objective of the signal processing is to filter out those noise and keep the useful information intact. That is one aspect of signal processing. There can be many more aspects. So for now let's be very specific on the word signal. So now this signal which we get is an analog signal. Why analog? Analog signal in the sense my voltage can vary from any minimum minus Vm to any maximum Vmax. It can take any level. So analog means, see, the amplitude of the signal is not confined to a particular level or to particular levels. It can take any value. So my signal can be 1.2 volts, 1.222 volts, it can be anything. So since the y-axis or the dependent variable axis or the amplitude axis is continuous within a range. It may be unbounded also, but we are strictly speaking of bounded signals. So because we want to implement them in digital hardware, so this kind of signal which can take any value between my maximum and my minimum, so this kind of signal is called analog signal or continuous time signal. Actually, continuous time signal, there are a very thin line between analog and continuous time signal. For example, say I have a square wave pulse where my time is continuous. So the signal is defined in all instances of time. It's either 0 or say 5 volt. So this is a continuous time signal, but we will not call it strictly analog signal because it has strict two levels. We can call it analog signals in some domain, but this is not strictly an analog signal. So this has only two voltage levels, 5 volt or a 0 volt. So it is a continuous time signal. But in many texts they refer this as analog also, but this is not strictly analog because the amplitude axis is quantized at two levels. But definitely this is a continuous time signal because it is valid for all time instants. You can say there are piecewise discontinuities at these edges, so but still this is a continuous time signal. So I think this clarifies the context of analog signal, continuous time signal. Now let's just refresh the concepts of digital signal and discrete time signal. So when we sample an analog signal, so now no more the signal is a function of time, it becomes a function of samples. This is the first sample, second sample, third sample, fourth sample, and so on. So we represent the sampled version of this analog signal or continuous time signal as a discrete time signal. Now this XSN is nothing but X of, so I take only integer multiples of my sample time. So if say sampling time is 1 second, so I observe this signal at say 0 second, 1 second, 2 second, 3 second, and so on. So this sampled signal or the discrete time signal is just observing the samples at these discrete points. For example, say today's temperature, it is a continuous signal, but we are not interested in observing the signal throughout. So we take the samples every 1 hour. So the sampling time is 1 hour, and at every sampling time we have a sample which denotes the X of XSN. Now this can have any value in the amplitude. So if we want to implement this in a 2-bit hardware, so we can have 4 levels, 0, 0, 0, 1, 1, 0, 1, 1. Or we can implement in a 4-bit hardware where we can have 16 such levels. So the idea is to have discrete amplitude levels. We quantize the amplitude levels, and once we quantize the amplitude levels also, we call that quantized signal as a discrete signal XN. Digital signal XN. So in digital signal, the independent variable is quantized or sampled, the discrete variable is also quantized. So to summarize, from a continuous time analog signal, we get a digital signal by first sampling the independent variable or the time and then quantizing the amplitude. Okay, thank you.